Okay, next we are thrilled to hear from Ren Yuxin of Huawei. He will discuss from hardware to operating system heterogeneity, practice, opportunity, and challenge. Ren, please go ahead.
Hello, everyone. So it's my pleasure today to share our research work about the heterogeneous system. Okay. Oh, thank you. So this is the outline of my today's talk. First, I will briefly introduce the overall background of the heterogeneous system, followed by our optimizations in our practice and in the open source community. So next, I will discuss a new system design for a new architecture about the memory interconnected rack scale machines. And finally, from the perspective of the large scale clusters, I will discuss some challenges in the managing and utilizing the heterogeneous system. So the heterogeneous hardware is very familiar to us. So it is now rapidly developing and widely deployed. So the heterogeneous hardware contains the various types or modules of the hardware, so including the CPU, a memory, bus, and storage devices. So therefore, we expect in the future, the whole system capability does not only depend on the amount of hardware resources or the devices, but also rely on the heterogeneous optimization and integration. So as a result, the design and the optimization of the operating system becomes the top important research problems in the heterogeneous system. So this is because, on the one hand, the heterogeneous system hardwares have different features and capabilities, and they require the operating system to integrate them together. And on the other hand, the upper level applications always utilize the operating system instead of the directly interacting with the hardware. So the applications also require the operating system to adapt to the capabilities of heterogeneous hardware. So as a result, we believe the heterogeneity should not limit it to the hardware level, but also should be manifested in the operating system itself. So because the operating system interacts with the various heterogeneous hardware and applications at the same time, so we think the operating system heterogeneity is inevitable. So furthermore, so this heterogeneity covers all the aspects of the operating system, from its kernel architectures to the system services, from its performance models to the security and reliability. So the forms of the operating system heterogeneities are also diverse, and the technology development is driving the continuous expansion of the scope of the operating system heterogeneity. So let's see some examples that are generating the heterogeneous OS. So the first, the different applications and the scenarios requires the domain-specific OS optimizations. So there's no single form of OS can achieve the optimal performance for all the applications. So we need the diversified OS designs and optimizations. So for example, as discussed by Professor Lomai earlier, we need some AI specific OS, all the operating system specific to the large language models and all the HPC applications. And we also have the mobile OS or real-time OS. So in the second, the academia research is constantly exploring new systems, such as microkernels. And more importantly, due to the recent advancement of the programmable system and AI-based tuning, so it becomes much easier for us to modify the system to generate different OS. So finally, from the production perspective, so we also often encounter the heterogeneous OS in our actual products. For example, we have OS with different distributions, configurations, or parameters. And we believe in the future we will have more and more heterogeneous OS. So while the scope of the OS heterogeneity is broad, so the key principle for us is that we need to properly match and manage the OS heterogeneity especially we need to match their heterogeneity with the hardware and the workload. So next, I will introduce some specific operating system optimizations in our practice. So since those optimizations are almost based on our open source community, let me first briefly introduce our OpenOLA open source community. So the OpenOLA is now the biggest and the fastest growing OS community in China. Currently, OpenOLA has support the more than 82,000 software packages and has around 20,000 contributors. Over the past 4 years, the number of the OpenOLA installation is over 6 million. Following the concept of the OS heterogeneity and diversity, so the OpenOLA has supported most of the mainstream hardware architectures, including the ARM, RISC-V, and the LongArc. Meanwhile, the OpenOLA also supports the mainstream applications such as AI, big data, NFV, and the cloud-native applications, and the serverless, of course. So compared to the traditional open source communities, the OpenOLA has two significant distinctions. So first, the OpenOLA community is a research-driven and focused on the innovation. So in the recent years, many papers on in various top conferences, including the OSDI, FAST, and the HPCA. So second, the OpenOLA focuses on the cross-level vertical integration and the full stack optimizations. So especially, as I will discuss later, the OpenOLA has the deep research on some important components that are rarely studied by the academia. So thus, the OpenOLA also brings some valuable and new research directions to both the academia and the industry. So in short, the OpenOLA has evolved from a basic OS distribution to an open source community, and now it has become an innovation platform. So next, I will introduce some specific research project in the OpenOLA. So first, let's say a new dynamic loader in the OpenOLA. So every applications use dynamic libraries, and more dynamic libraries are shipped by the vendors and used by the application. So as shown in the right figure, a single application can rely on from tens to hundreds dynamic libraries. And the dynamic loader, it loads and links the dynamic libraries of a single application during the application startup. So however, as I said earlier, we simply treat this dynamic loader as a basic tool without a deep research. So due to the lack of the cross-library optimizations, the dynamic loader has a significant impact on the performance, on the application performance. And unfortunately, existing research is not sufficient to delve into these performance issues in the dynamic loader. So here, there are two performance issues we identified in our productions. The first issue in the dynamic loader is that each dynamic library are independently loaded into the application. Thus, they are spread to the various memory locations. As a result, those dynamic libraries cannot efficiently utilize the continuous memory huge pages, which degrades the memory performance. The second problem is of the dynamic loader is from the indirect function calls. So the dynamic loader cannot statically determine the function address at the compile time. So the applications have to use multiple indirect jumps to invoke the functions in the dynamic library, which incurs the extra overhead. And more important, those extra overhead occurs upon each function calls, which significantly reduce the whole system performance. And we have redesigned the architecture of the dynamic loader to solve these problems. And we enable this loader to support the cross library optimizations. Here we list two optimizations. The first optimization is called the library concatenation. So in this optimization, as shown in the first figure, we first split each dynamic libraries, and then we concatenate the same segments from different libraries into the memory huge page. So in this way, we achieve the efficient memory performance and usage. And the second optimization is called relocation branch elimination. So this optimizations rewrites the application binary during the loading process, and to replace the indirect function address with the real function address, which achieves the same effect of the static linking. And moreover, those optimizations are transparent to the applications. So we tested them over 20 applications, and it shows that our optimization can improve from 4% to 30% performance. So more technical details, please refer to our paper published in the OSDI 22. So next, I will introduce a new system auditing framework. The system provenance and auditing is a KOS component that is defined against the advanced persistent threat and attacks. Its core workflow involves the monitoring, collecting, and detecting the system behavior. So while there are some popular auditing tools in production, such as the SysDig and the Linux Audit D, but the research about them is not enough. So in our practical use, we identify the auditing framework itself has some serious security risks. The first security threat, we call it the flood attack. So with this attack, the attackers can generate a large number of auditing events to exhaust the storage buffer in the kernel, which forces the auditing service to drop other critical or sensitive events. And the second security threat is called the super producer attack. So the attackers can amplify the CPU utilization by keeping the auditing service busy and to content the CPU resource with other applications and degrade the whole system performance. So the root cause of these security problems is that the centralized architecture of existing auditing service breaks the logic and the resource isolation between applications. So thus, our key insight to solve these problems is to ensure each application use the isolated and independent resource quota to process its own auditing events. So the left figure presents our architecture of the new auditing service. So in our design, the auditing service is no longer an independent process, and it becomes a part of the application and is dynamically loaded by the OS. So in this way, the auditing service naturally inherits the isolation capability and scheduling resources of different applications. So as a result, a malicious process can only affect itself and will not damage other applications. So for the concrete implementation detail and its effect, please refer to our Yuxin security paper in the 2023. So now let's look at the OpenOLA improvement in the real-time domains. With the real-time applications, the real-time guarantees and the execution predictability is very critical in many areas, such as the autonomous driving and the robotics. So the cross-core performance interference is one of the top threats to the real-time guarantees. So the cross-core performance interference means that the execution on one course causing various timing delays to irrelevant executions on another course. And unfortunately, currently the Linux kernel itself becomes a major source of the cross-core interference. So even with the existing real-time enhanced Linux, the RT Linux, we measured its the interference latency is close to the 50 microsecond, which cannot meet the hard real-time customer requirement. And more seriously, so many the Linux kernel components have these interference problems. So we cannot rely on a single fix to solve all the problems. So here we list two typical interference problems in the Linux kernel. So the first problem comes from the kernel worker queues. The worker queue is a lightweight kernel task management module. So sometimes the worker queues may mistakenly wake up the kernel tasks on the isolated real-time cores. So as shown in the first figure, this wake up brings a lot of unnecessary interference, so including the API handling and the context switch on the isolated cores, which delays the real-time application execution. Similarly, the second example comes from the ASID management. The ASID is a type of shared hardware resource, but this kernel failed to properly isolate those resources between CPUs. Thus, the one core can flush the ASIDs to generate the blocking and the TLB overhead on another core, and then affect the real-time or critical application timings in the isolated cores. So there are many other similar issues in the Linux kernel. And over the past 6 years, the OpenOLA continued to improve the real-time capability of the kernel by fixing more than 30 interference issues. So the OpenOLA now gets better real-time performance than other distributions. And we tested it using in robotic scenarios, and it shows the OpenOLA can achieve 1.6 times improvement over the current RT Linux. And more the details can be found in our RTSS paper this year. So our experience shows that the collaboration between the academic community and the Linux community is important. and we encourage more researchers to engage with the OpenOLA. So next, I will introduce a new system design for the new architecture about the rack scale memory interconnections. So the memory interconnect is a new type of a bus that enables the computing resource within a rack to access the global shared memory using the load store semantics. So this significantly enhances the rack scale, the memory capacity, computing scalability, and the resource elasticity. However, existing the disaggregation-based system fail to efficiently utilize these shared memories and to achieve the shared OS services. So let's see some details. So in the left figure, the existing disaggregated systems always rely on the RDMA-based networking to integrate the pools of different hardware resource or devices. But the rack scale machines has notable distinctions. So the rack scale machine connect the general purpose computing together, and each computing node actively executes OS instance to manage the global rack resource. So ideally, we expect the entire rack to be operated as a single computer, that all the executions are based on the memory access. However, to achieve the rack scale shared and unified OS functionality faces several challenges. The first, the rack scale synchronization is difficult. So this is because the global shared memory has higher memory access latencies, making the frequent access on the critical path impractical. And even worse, the rack scale shared memory does not have the hardware-enforced cache coherency support. The reliability is the second challenge. The memory faults in the rack scale machines becomes more frequent because the extra interconnect hops and switches increase the fault probabilities and the surfaces. And the third challenge is the compatibility. So to leverage the shared memory while keeping the compatible OS functionalities, so we need to place a part of the kernel functionalities and the data structures in the shared memory, in the shared global memory, and then coordinate with their private states with the local memory. So to solve those challenges, so our key design principle is to co-design the synchronization and the fault tolerance mechanisms for the non-cache coherent shared data. So this figure presents our design overview, which contains 3 layers. The first part on the right is a development kit. So this kit consists of a set of the common mechanisms and primitives to develop the rack scale system services and applications. So especially the kit has a lock-free synchronization algorithms that do not depend on the hardware cache coherency support, and some basic memory allocation and placement facilities to optimize and coordinate between the local memory and the global memory. So the kernel on the left implements the critical OS functionalities and coordinates with the node local OS instance. So this requires us to redesign most of the key kernel subsystems, including the scheduler, file systems, and the communication systems. So finally, we ensure the whole system reliability via new system abstraction called the fault box a fault box vertically consolidates the memory and the states of an application based on the application's execution flow to minimize the failure radius and achieve the rapid recovery upon the fault. So finally, let's focus on the cluster-wide and discuss some challenges in the heterogeneous system. So as I discussed earlier, there is no a single perfect OS can fit all the scenarios. So as a result, the multiple different heterogeneous OS is unnecessary to coexist in a cluster. However, existing cluster level management is completely unaware of the operating system heterogeneity. So current cluster management typically assumes that all the nodes deploy the same OS instance and completely ignore the difference and the features of those different OS throughout the entire process of the task scheduling and the resource management of the cluster. However, the effective and fine-grained heterogeneity awareness and management in the cluster-wide faces some challenges. So first, the modeling and analysis of the OS heterogeneity is difficult. So this is because the OS has too many parameters and dimensions, and the difference among them are very subtle. So this figure demonstrates the impact of a single parameter variation on different applications. So we can see that the different OS configurations have different impact on different applications. So this requires us to have a very accurate understanding of the OS capabilities in order to correctly utilize the heterogeneous system. So the second challenge is matching and scheduling the OS heterogeneity. However, this matching and scheduling is necessary to ensure the large-scale application tasks are distributed to the suitable OS instance. However, existing the experience-based tuning and the heuristic scheduling algorithm cannot meet the scheduling and coordination requirements between the heterogeneous OS. So this figure illustrates the performance of an existing cluster job scheduler. So it is evident that existing cluster job scheduler cannot properly match the tasks with a node of different OS. So which results in the cluster performance being much worse than the theoretical best scheduling and the optimal performance. So to solve those challenges, we needed to reconstruct the entire cluster management workflow and introduce the heterogeneity awareness across all the flows and the modules of the cluster management. And furthermore, the heterogeneity awareness requires multiple techniques, including the heterogeneity detection, representation, measurement, and matching. So there are more other challenges in the heterogeneous systems, such as the development and the maintenance. So we will continue this discussion this afternoon during our panel discussions. Thank you all for your listening. And Huawei and our research are very open, and we welcome any type of discussions and cooperations, such as the paper collaboration or the open source collaboration. Thank you.
Okay, thank you, Ren Yuxin. Any questions? Okay.
Thank you for a great talk, Ahmed Ali Din, Huawei also, but another more. So I think in your slide 23 or 24, you were basically talking about in the rack management for the rack scale management OS. You're talking about memory pooling, basically, where you would try to give a unified memory interface. So I think it's slide 23 or 24. However, many of the current applications, for example, training applications, TensorFlow and PyTorch and many of these platforms, they do quite a bit of the actual memory management today. So sometimes I feel like the operating system is being put to the side while the application layer is doing a lot more of the memory management for training and inference, and in the case of machine learning workloads. Database management systems also now have quite a bit of memory management internally, and so are a lot of these power applications. So what is your view about the future of basically trying to provide a single interface for memory pooling, while the applications themselves actually do a lot more memory management than they should?
Thank you. So that's true. So there's more and more the applications, especially the large scale application frameworks, do their own management. It's not only limited to the memory management, actually some task scheduling as well. So my thing is this. So there are two things. Inside the application, the management mechanisms, they sometimes still reuse some things from the operating system. Basically, it just moves this mechanism from the kernel to the application itself, right? And sometimes the application developers is not very familiar with such a low-level management. So they're still relying on the OS communities to optimize and design their technique. Even this code is running inside the applications. So this is still valuable for the OS communities. And this is a similar thing that we can see this in a lot of papers, right? So for example, in the OSDI, we do have the such stuff, but still in the published in the OS conference. So I think the technique itself is the most important. It's not very related to where it's running, and it's really relying on the OS related technique to optimize their management.
Okay, thank you, Yuxin. Any further questions? Okay. Yeah, thanks for your talk. I'm just wondering, what's the use case for having heterogeneous operating systems on a single cluster? Is that something which is common in Huawei? Because typically you would have some version, some flavor of Linux that's just deployed over everything, and then you would have some kind of container orchestration that would run on top of it.
Okay, yes, good, great questions. So there's two cases here. So let's first look at the scope of the heterogeneous operating system. So in the real case or in the real productions, look at the right side. Even the clusters may have the similar operating systems, but with different configurations or distributions. So this is very common. So in the previous, people think this is maybe a bad thing. Mm-hmm. But if with from the heterogeneous management perspective, this may be good because the different operating even the different versions may have different trade-offs, right? So we can utilize the best part of each of them. So this is one case. It's a similar system with different with the difference. Another thing is that even with the single clusters, each node executes different jobs. For example, in the big data, that we have different tasks. They belong to the same applications, but they have different functionalities. In this case, they require different the OS optimizations. So we also need to can have the heterogeneous OS in the same clusters. And we also have some experience with the HPC application for this. It's not widely deployed, but I think we can try to, this may be a trend in the future.
Okay, thanks. Yeah, we can maybe continue that offline because I'm just interested in the use case. Okay. Thanks. Okay, thank you. Any further questions or for online? Okay, as we mentioned about the OpenOLA, we have experience boost outside. You can experience during the launch time. Okay, that's all for the half day's topic. And thanks for listening again. Thanks for your wonderful topic. Okay.